In this video, we're going to talk about types of solution sets for linear equations. So here's a quote. I love it. Science is what we understand well enough to explain to a computer. Art is everything else. So we're going to define what a consistent system is. It's a system of linear equations in which it has at least one solution. So it could have an infinite number of solutions, but it has at least one solution. Otherwise, the system is called inconsistent. So if we take a look at our equations here, it becomes this augmented matrix in which each one of those coefficients match the rows, and then of course the constants are on the other side of that straight line. If we go through the process of the reduced row echelon form, we end up with this equation, or this matrice right here. So let's talk about this matrice. So R, if we remember from yesterday's video, represents a number of rows that have leading ones or are pivot columns. In this case, this is a pivot column, and this is a pivot column, because those are the two rows in which I have a leading one. Zeros on the left-hand side. Now, these subscripts d sub 1 and d sub 2 is column 1 and column 2. So if you remember from yesterday's, these are the representations of which columns have our pivot columns. And then we subscript and we do F for our free columns, or in other words, the ones that don't have a leading coefficient of 1 in that column. And that would be this column, and technically this column. Even though that is coming from the constants, it is still a column that does not have a leading 1. Now, the reason we talk about that is because it's going to help us in this section. So our D, which we know from yesterday's video, D1 and D2, is 1 and 2. Again, this represents column 1 and this represents column 2. And our F is the F1, F2, F3, columns 3, 4, and 5. Now notice on this particular example that none of these sets have numbers in common. None of these sets have numbers in common, and it also accounts for all the columns in A. And we see that these sets are a partition of the set of column indices, and we'll talk about that later. So what we know is that the variables that correspond to the leading columns, we call those leading variables, or dependent, or you might even hear them as basic variables. The non-leading variables are called free variables. So you hear it being referred to as free or independent or non-basic variables. So to find all the solutions to the system, we are just going to solve the equations for the leading variables in terms of the free variables. Now what we know is that this comes from x sub 1, x sub 2, x sub 3, x sub 4, and these are my constants. So the equations that I have left over from this first row is x sub 1 plus x sub 3 plus x sub 4 is equal to 3. And then from the second row, I'm going to get x sub 2 plus 3x sub 3 minus x sub 4 times x sub 4 is equal to negative 2. And what we know is our free variables are x sub 2 and x sub 3. So what I do then to find the solution, and I know this is a consistent because this here is a row of zeros, it is a consistent solution, that my x sub 1 is going to be dependent on my free variables. My columns, my pivots, are dependent on the free variables. So I'm going to take these equations here and solve for x sub 1, and I'm going to solve for x sub 2, because those are my leading variables. Those are my non-basic variables. So what I'll do then is I'm going to take this and solve for x sub 1. So x sub 1 is equal to 3 minus x sub 3 minus x sub 4. And then my x sub 2 is going to be negative 2 minus 3x sub 3 minus 4x sub 4. Now, order in and of itself doesn't really matter, but we typically will put our constant first and then our variable second. What the solution set could be represented as is this. S is equal to, use a big curly bracket, and then you write it as a column vector, where my x sub 1 goes in the first slot, which is 3 minus x sub 3 minus x sub 4. My, excuse me, my x sub 2 is going to go in the next row of my column vector, negative 2 minus 3x sub 3. And I didn't give myself enough room, so give me a moment to erase that, and I'll just erase all of that. So let me try this again. So 3 minus x sub 3 minus x sub 4. My x sub 2 is my next row. So negative 2 minus 3x sub 3 minus 4x sub 4. My x sub 3 was my free variable, so that is x sub 3. And my x sub 4 was also a free variable, so that's x sub 4. So then I put a straight line so I can tell you all about my free variables. My x sub 3 and my x sub 4 comes from the complex numbers. And remember, we talked about that. Stop panicking. It's for this class mostly going to be in integers, definitely going to be most of the time in reals. Now, the other way that this could have been represented is it could have been represented in terms of column vectors, where s is equal to my first column vector would be 3, negative 2, 0, 0. These are the constants. And then plus x sub 3, and now I'm going to take the coefficients off the x sub 3 out of each one of those equations. So negative 1, negative 3, 1, and 0. And then plus x sub 4 and all the coefficients on the x sub 4, which is negative 1, negative 4, 0, and 1. So that is also another way to represent the solution. So we define dependent and independent variables. Suppose A is an augmented matrix of a consistent system of linear equations, and B is the row equivalent, so like our example up above. So suppose J is the index of a pivot of the column of B. So in this case, an index on my example up above would have been the 1 in here and a 1 in there. So my J would be 1 and my J would be 2. Then the variable x sub j is dependent. So that would have been my x sub 1 and my x sub 2. Those are dependent. A variable that is not dependent is called independent or free. So let's take a look at this example. Now my pivots happen at my first column, my x sub 1, my second column, or my x sub 2, my third column, the x sub 3. Now this is an augmented reduced row echelon form. And then in my x sub 4, I don't have a pivot there. So my x sub 4 is independent. My x sub 1, x sub 2, and x sub 3 are all going to be dependent on x sub 4. My equations, again, are this. I have x sub 1 from the first row plus 2x sub 4 is equal to 3. My second row is x sub 2 minus 3x sub 4 is equal to negative 5. And my third row is x sub 3 plus 4x sub 4 is equal to 7. And as before, I am going to solve for x1, x2, and x3 in terms of x sub 4. And when I do that, I've got x sub 1 is equal to I do the constant first, 3 minus 2x sub 4. X sub 2 is equal to negative 5 plus 3x sub 4. And x sub 3 is equal to 7 minus 4x sub 4. And I can write my solution set in this form as before. So the solution set with the curly bracket, a column vector, 3, negative 2, x sub 4, negative 5 plus 3x sub 4, 7 minus x 4, x sub 4, and then of course x sub 4. And then I'm going to tell you where x sub 4, because that's the free variable. X sub 4 comes from the complex numbers. And as before, I can write it as I did before. So S is equal to, my first column vector will be all the constants, which is 3, negative 5, 7, and 0. Plus, this time I'll have an x sub 4, one free variable. So now I pull off the coefficients off that, which is negative 2, 3, negative 4, and 1. And so I can represent my solution set this way as well. Our next theorem here says, suppose A is an augmented matrix of a system of linear equations with n variables. Suppose also that B is the row equivalent matrix, so it's been in reduced row echelon form, with R number of 0 rows. The system of equations is inconsistent if and only if n plus 1 of B is a pivot column. What does that mean? Well, it means formally that if you have a row of zeros with the exception of the last entry, then you have a no solution system, so in other words, it is inconsistent. So using that information, I'm trying to determine which one of these are consistent or inconsistent. In this example here, I see that I don't have a leading zeros in the last row and then a constant in the last position. So this one is consistent. But on my next example here, remember these are augmented matrices. My next example here, I've got this false statement right here which says 0 is equal to 1. And it is then pointing back to this theorem stating that if I have a row echelon form, a reduced row echelon form, my B matrix, which is what is here, if I have the system of equations is inconsistent, even only if the column of n plus 1, so in other words, my very last column is a pivot column. In this case, that's a pivot column because that's where I see the 1 is in the very last column. So we know that this one is inconsistent. Okay, let's take a look at some more theorems, more for less. So if we take a look at our next theorem here, consistent systems are in N. So we already know it's consistent. Suppose A is an augmented matrix of a consistent system of linear equations with n number of variables. Suppose that B is the row equivalent matrix in reduced row echelon form with R number of pivot columns. Then R must be less than or equal to n. If R is equal to n, then it has one unique solution. If R is less than n, then it has infinitely many solutions. So you're asking yourself, what does that mean? Well, what that means then is it allows us to look at R and N and make a determination of the type of solution we expect to get. So let's take a look at these examples here. With these examples, using this theorem that I have, I'm going to determine what kind of systems or what kind of solutions I expect. So I'm going to look first at my R, and my R here is my pivots. 1, 2, 3. R is equal to 3. And these are in reduced row echelon form. So that means I have 1, 2, 3, 4 variables. So my n is equal to 4. Since R is less than 4, then I know I have an infinite number of solutions. Now, I'm gonna solve for this in just a moment. Then I'm gonna just take a look at B, and then I'll come back and solve. I'll just solve for B first because it's easier. And the reason I say it's easier is because in this one, my R is equal to 1, 2, 3, 4. R is equal to 4. And my N is equal to 1, 2, 3, 4. So my N is also equal to 4. Since R is equal to 4, and N is equal to 4, then R is equal to N, which means I have a unique solution. And in fact, I know what that unique solution is. That unique solution comes from each one of these. So this bottom row gives me that x sub 4 is equal to 2. The next row, x sub 3 is equal to 0. Next row up is x sub 2 is equal to 4. And the next row up is x sub 1 is equal to 1. A unique solution. So I could write it as a column vector of s is equal to, and it is going to be 1, 4, 0, and 2. Let's take a look at the other one that I kind of skipped over, and I know that it's going to be an infinite number of solutions. And so that tells me that I have a free variable. The free variable is the one that does not have a pivot in the column, and so that is column 4. So my free variable, just like before, is x sub 4 is my free variable. That means everything is going to be in terms of x sub 4. So I'm going to take my first row down here on the bottom, and I have x sub 3 plus x sub 4 is equal to 2. X sub 3 is 2 minus x sub 4. This next row here tells me I have x sub 2 minus x sub 4 is equal to 2. So that tells me that x sub 2 is equal to 2 plus x sub 4. And then, of course, my top row, let me go just move that over here. My top row is going to give me x sub 1 plus 2 x sub 4 is equal to 4. And so I solve for x sub 1, and I have x sub 1 is equal to 4 minus 2 x sub 4. So my solution set is going to be, first I'm going to write it in this form. I'm going to do it as a column vector. My x sub 1 is 4 minus 2 x sub 4. My x sub 2 is 2 plus x sub 4. My next one is 2 minus x sub 4, and then my last one is x sub 4, such that x sub 4 belongs to the complex numbers. Similarly, I can write this as s is equal to, first my constants, 4, 2, 2, and 0, and then plus x sub 4 and its coefficients, negative 2, 1, negative 1, 1. Okay, let's take a look at my next theorem. Woo! Theorem. So suppose A is an augmented matrix consistent, and you're going to hear this over and over again, so I'm just not going to read that part of it. Let's get to the meat of it. The meat of it is that in this one, suppose blah, 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 with R rows that are not completely zeros. Then the solution set can be described with n minus r free variables. What this does is it allows us to determine how many free variables we expect to find. So as I take a look at this example, and it's asking me to use that theorem to determine the number of free variables. So I look and I say, okay, I have 3 variables. This one has 3 variables. That's the 3 there on the left side of that augmented part. So I have 3 variables, which is what my n is. And I look at my pivots, and I have 2 pivots. So 2 pivots, or in other words, 2 r's. These combined with that theorem says I have 1 free variable. Okay? Now let's take a look at the next one. So my next one, I actually can't use that theorem on because this is not consistent. And the reason I know it's not consistent is because if I do this bottom 2 rows are false statements. 0 does not equal negative 36. 0 cannot equal 16. So I can't use that theorem, my previous theorem up here, on this because it's not even consistent. So let's take a look at my next theorem then. So my next theorem states that a system of linear equations has no solutions or unique solutions or infinitely many solutions. So this is just wrapping up that these are our 3 choices. We get a unique solution, we get a no solution, and we have a finite or infinite many solutions. So let's take a look at this decision tree in terms of the theorems that we have learned. The very top of our decision tree is theorem RCLS, which is recognizing consistencies of a linear system. So then after we recognize it, we're going to branch in one of two ways. No pivot columns in the column n plus 1, then we are consistent. And then we go down to the next theorem. So I'm going down this side. It's consistent. And here I am going to use this theorem, which is the one we just did. Consistent systems R and N. And then I'm going to go and decide from there which one is true. Is R less than N? Then we have an infinite number of solutions. Is R equal to N? Then I have a unique solution. I'm going to get one single unique solution. Going back up here, going down this branch. The pivot columns in column n plus 1, if that happens, it's inconsistent and I don't get any solution. So let's move on. Our next theorem is consistent, more variables in equation, and infinite solutions. What this does is it allows us to look at the system of linear equations and determine if the solution will be consistent or not without doing much work. So I'm going to take a look at my examples here. I'm going to determine if the previous theorem applies or not. Now what the previous theorem applies is the consistent more variables than equations. Now I know for this very first one I can't use that theorem. That's a big old no, because of the fact that this last row here makes it inconsistent from previous theorems. So I can't use this theorem on it because it has to be consistent, and I know that this is inconsistent, so it has no solution. But can I use it on this one? And the answer is yes, because if you have more variables than you have rows, then you are going to have an infinite number of solutions. I have my first variable, my second one, my third one, my fourth one, my fifth one. There's my constants. I have 5 variables, but I only have 3 rows. So then it's a matter of determining how many pivots do you have. I have a pivot here, an x sub 1. So my pivots, D1 is 1. My second pivot happens here in the third column. And then my third pivot, D3, happens here in my fourth column. My free variables happen in column 2, so f sub 1 happens in column 2, so that's 2. And my second free happens in column 5. So that tells me my free variables are x sub 2 and x sub 5. And my dependent variables are x sub 1, x sub 3, and x sub 4. So that whole D and the subscripts and the F and the subscripts, what we're really doing is subscripting. I know that in this case, this is x sub 2 is a free variable, and because I have an F subscript, and I have an F with a subscript, and this is x sub 5. Those are my free variables. What that tells me is when I go to find my solutions, I'm just going to move this over. I'm going to have my solutions here, and then I'm going to have something with my constants, and then I'm going to have my x sub 2 and the coefficients on the x sub 2, and then I'm going to have my x sub 5 and my coefficients on the x sub 5. So that's what that solution is going to be. So this is the last wrap-up of the video here, and it's saying how do you solve a systems of linear equations. The first thing you want to do is figure out what your n is. How many variables do you have? You go ahead and do the augmented matrices, and you put it in the reduced row echelon form. After you do that, you use the theorem REMF. Identify the pivots and the number R. So we want to know the pivot columns. We want to know how many pivot columns we have. And then we know that if n plus 1 is a pivot, that's basically saying your last column is a pivot, then we know the system is inconsistent and we stop. If that last column is not a pivot, then either I have a unique solution when R is equal to n, the number of pivots equal the number of variables. If that's true, I have a unique solution. If R is less than n, so I have less pivots than I have variables, then I have to use my theorem RCLS up above, and I'm going to have an infinite number of solutions. So that's it. That's this video.